lecture. We have two sessions today. So first is guest lecture from Professor Yen-Ming Chen, okay, from National Sun Yat-Sen University, Taiwan. Okay, and then the second will be the introduction program, introduction session from for a double degree program. Okay, for bachelor, both and master program. So hopefully this morning you can enjoy the guest lecture. And then if you want more information regarding the program, you can directly ask to Professor Chen. Also, maybe you can ask to Miss Kathy. Miss Kathy is from International Office from National Sun Yat-sen University in Taiwan. Okay, hopefully you can have a fruitful discussion this morning. And also thank you for Bu Endang. Okay, thank you Bu for your coming. And then also for other maybe colleagues already here. Also from the participant who is in online and Zoom meeting. Okay, hopefully you can enjoy the meeting, the guest lecture and the introduction session for the program this morning. Okay, now I will give the time and the floor to Professor Chen. Professor, please. Yeah.
Sorry for my pronunciation. Yeah. And professors and students from an ITSWE department. Very glad to see you here. And I'm the lecturer today. My name is Yen-Ming Chen from NSYSU Taiwan. And I'm very happy to have this opportunity to present my research and to you. And I wish you to know more about me, my research, and my university in Taiwan. Okay, first of all, I want to give you a brief introduction to myself. Okay, my name is Yen-Ming Chen, and I'm from National Sun Yat-sen University, Taiwan. And I'm currently an associate professor. And I'm also currently the chair of the director of International Master's Program in Telecommunication Engineering. So my specialty is in telecommunication, and my research interests are mainly about the wireless communication and also the non-orthogonal multiple aces. If you are familiar with the contents in 6G communication and beyond, you will be able to know that this is an important issue in the future communication systems, the NOMA, non-orthogonal multiple aces. And also, I'm also good at error correcting codes. Yeah. Does anyone know what is error correcting code? Anyone? Error correcting code? No? Okay, I will give you a brief introduction about the content, the idea of error correcting codes. And also some coded modulation. Yeah, you know, modulation is something if we want to transmit our signals into the channel, we need to do the modulation first, right? So my specialty is combine the design of coding and modulation, and also do some biometric crypto system. Okay, so all right, so this is me, and I have some honors recently received from the IEEE IT Society and Communication Society Taipei and Tainan chapter. I have received the Best Paper Award for Young Scholars, and I also received the IEEE Tainan section Best Young Professional Member Award. So these are some honors I have recently, and this is my website. There's some details of my published journal papers. So it's about my research field. If you are interested in it, you can check on my website. All right. So I want to briefly introduce to you some of my research results. This is some scope of my research. The first is the non-orthogonal multiple aces, which is exactly the topic we are going to talk about today. So the multiple aces means that there are several users want to share some common resources. Okay, we'll see about this later. And for each users, because you see the transmitted signal is actually the superposition of data from different users. So how to properly combine them is very important. Okay, if we can properly design the signal of individual users, then after the combination of the transmitted signals, we can do properly design, and so that we can recover them at the receiver end properly. So the idea is like this. So how to properly design the mapping is very important. So this technology is called the Sparse code multiple access, which is a very important new technology in 6G communication and beyond. Okay, so in this research field, I just designed a codebook for different users, and I can use conventional design technology, or I can use some machine learning based technology. For example, we can use the reinforcement learning or deep learning technology so that I can design the codebook and the constellation, the signal used for different users. So as you can see, these are the signal constellation, signal points utilized for different users. It seems to be random. However, these are some design signals, so that the signal for individual users can properly combine with each other. Okay, so these results have been published in some IEEE papers, including the IEEE transition communications, transition wireless communications, and also the transaction on vehicular technology. Okay, so the other research field I am interested in is about the error correcting codes. So what is the error correcting code? If you are not familiar with this idea, error correcting code means that before the transmission, I can add some redundancy into the transmission signals. Okay, so except for the thing I want to transmit, I can add some additional bits with these informations. These additional bits are not added randomly. They are designed, which means that they are correlated to the signal you are going to transmit. So using the relations between the redundancy bit and the message bit, we can recover and correct the error induced by the channel. This is the idea of error correcting code. So if you are familiar with the 6G communication, you will know that there is a new code called the polar code. So the polar code is a new code utilized. It has been included in the 5G spec. Okay, so it's actually used in now the communication system nowadays. So what I do is to develop new polar decoders, because the structure of this code is very, very unique, so that the design for the efficient decoder is still an open problem. So what I do is to design a new decoder that is based on belief propagation. The belief propagation means that we can propagate some soft values inside of this figure, so that I can achieve a very excellent performance, a BER performance, however, with a very low decoding complexity. So this is the idea of this research field. This is just a easy, simple introduction, so I don't want to go to the detail of this, but the idea is I'm designing new decoders for the power codes, which is the new code for the 6G communication and beyond. Okay. And the other scope is that this is very interesting work. My research, because I have a wide range of research interests, this is to do the biometrics. So what is a biometric? For example, your fingerprints, your iris, these are biometrics. So inside of these messages, these features of your body, it contains your personal information, so that it can be used for identity recognition. Okay, so for example, if you use your phone, you use face recognition, right? So we also have a fingerprint recognition or iris recognition. My specialty is for the iris recognition, and I can combine the iris recognition with the error correcting code. So you may wondering why we need to combine with error correcting code. It is because, for example, if you enter your biometric in the database, so the next time you need to, when you want to access this system, you need to enter it again, right? So the system will compare the current input information with the information stored in the database. So if they match with each other, then your identity can be identified, right? But the thing is, because of the feature of the biometric, the biometric entered in this system every time will have slight difference. Okay, the slight difference makes the system think that you are actually a different person. So how to correct the slight difference between two inputs? We can use the error correcting codes to correct these things so that the system can successfully perform the identity recognition. So that's the basic idea of this work. So I use the idea of error correcting codes, which are a very important technique in telecommunication. I apply it to the research field of iris crypto system, so that we can build a very good system, have excellent recognition performance, however, with a high level of security. Okay, so that's the basic scope of my research field. So I hope there are some little inspiration for you. If you are interested in any research topic, you can maybe you can contact with me and also ask for some further deep questions. So we come to today's topic. Today's topic is about the design of near optima sparse code multiple aces, which is a codomain NOMA for 6G and beyond. So I know most of you are. I'm not sure. Are you undergraduate students? Do we have any postgraduate student here? Most of you are undergraduate, right? Yeah, that would be a little bit difficult because Dr. Judin tell me that you are an undergraduate student. However, my research topic is a little bit complicated, so I decided to skip all the mathematical derivations, and we only focus on the ideas. And for the first part of this talk, I will go to the idea of why we want to do that. And then for the second part, I will only talk about the results. Okay, what contribution we have and what the idea of why we can do this, and we skip the mathematical part. Okay. So, sorry for the previous. So this is the outline today. I will introduce the system model and what is the NOVA and why we need a NOVA, and we will use the case for AWGN channels. Do you know what is AWGN channels? When you transmit something, you encounter some noises. The noises can be modeled with AWGN, the Gaussian noise. Okay, so in the Gaussian AWGN channels, we use this as an example to demonstrate how we design an SCMA system. But the thing is, the cases for uplink and downlink channel are more complicated. Okay, so to understand this part, you need to have some background knowledge about the wireless communication system, the fading channel, something like this, and you need to have some background knowledge for about the analysis for pairwise error probability. That is more complicated. So for this part, I will only introduce the result to you. Okay. All right. So this talk involves several papers I have published recent years. Okay. So if you are interested, you can go to you can check search for my name and read the related publications. Okay. So non-orthogonal multiple aces, we call it NOMA, is a promising scheme that achieves large-scale connectivity, low latency, and high spectral efficiency. Okay, so I will talk about this later. And the technique we focused, which is called the sparse code multiple aces, is a codomain NOMA, a spatial NOMA system. Okay, so in this system, we have several users. Each of them are assigned with a dedicated designed codebook to directly map their message bit to a multi-dimensional code word. Okay. Next thing. Okay. So because the sparse means the feature of this signal type, there is a feature sparse. The sparse feature makes it possible to use some message passing decoders so that we can have to decode this system with a very low complexity. However, the receiver is not the design. It's not the thing we want to introduce today. So we focus on the transmitter. So the key factor that affects the performance of SCMA lies in the design of its codebooks. Okay, so we are going to talk about the design of the codebook today. So I will introduce the, so actually this slide is has lots of contents, and it actually contains the design criteria for CISO, which means single input, single output, which means that the transmitter and the receiver only have one single antenna for both of them. We discussed the design criteria for CISO SCMA codebooks, considering AWGN, uplink, and downlink fading channels. We actually have accomplished the design for several different kinds of channels, but we will only focus on AWGN to introduce how we do it. Okay, so I think this is the details. Maybe you can skip this. And eventually I will introduce some AI-based technology for doing this. Okay, so why NOMA? So these are the figures of conventional orthogonal multiple aces. So when we talk about orthogonal multiple aces, it means that we have in the base station or in the system, we actually have multiple users. We have many users which to transmit through the channel. So the base station needs to properly assign the data for different users so that they will not interfere with each other, right? So I suppose you learn there's a system called TDMA. You might learn in your the course of a communication system. Okay, the TDMA means that the base station can properly divide the time resource into several sections. So each sections are occupied by a single user. So the first user uses the first time section, and the other user. So you can see for the access of time, it's divided into several sections. So each user can use at this section, at a single section, each user can use all the frequencies to transmit the signal. And all the users use the same power for doing this, okay? So another similar result is for the FDMA system. So instead, we cut the frequency component into several sections. So for example, we can use OFDMA. We have an OFDM system. Different users use different subcarriers to transmit their data. And because we use the orthogonal frequency of DMA, so the data for different users, different sub-channels will not affect with each other. If we are talking about a slow fading channel, they don't affect with each other, right? Okay. But for each user, you can use a period of time for the transmission, and they all use the same power. Okay, so we also have CDMA. Each user use different time and frequency. However, they just overlap with each other because every user are assigned for a CDMA codebook so that they are orthogonal with each other. So there will be no interference between users. So these are the conventional multiple aces we have. So why NOMA? It's because for the since the 5G communications or 6G and beyond, we have more and more user connectivity. So we have a larger number of users, but however, the resource, no matter the time resources or the frequency resources, are limited. So we wish to add more users within limited resources. So how can we do this? The resource is limited. However, the number of users grows. So how can we put more users into limited resources? So in this situation, we allow some limited interferences between the users. For example, if you use FDMA, we can cut the frequencies into more smaller pieces, right? But if you cut it, if you put more possible pieces here, maybe the sub-channels start to interference with each other, right? So the orthogonal, the property of the orthogonal is destroyed. We have some interferences. However, we can put more users here. right? Or you can put more codes, more different codes here, because what we talk about are orthogonal codes between each other, so they don't have interferences. But if you put more codes here, there are some, because the design of code cannot be so good, so there are some interferences. So the idea of NOMA is to put more users into limited resources. Okay, so SCMA is one of the technology for doing this, but it's a little bit complicated, so I use this simple figure to introduce the idea. For example, now we have 6 users, okay? So each users have one codebook. So what is a codebook? For example, for this user, firstly, I want to explain. This axis means the resource. So we actually have 4 resources here. But for this user, it only used the 2 of them. It used this resource and this resource, the first and the third resource. So for the second user, he used the second and the fourth resource, okay? So you can observe that within a single user, for single resource, for example, the first resource, we actually have user 1, 3, and 5 use the same resource, right? But for example, for user 1 and user 3, although they have shared one common resource, however, the second one is different, right? So you can see there are no 2 users have exactly the same resources, right? They differ at least one resource, okay? So now we can see we have 4 resources. However, if you use OMA, you can only put 4 users here. However, now we can put 6 inside of 4 resources, right? We can put 6 users into 4 resources. So there would be some interference with each other. However, if we can design the codebook they have in the receiver through the technology of message passing decoder, we can gradually recover the original message without severe interference. Okay, if we have enough power, we can mitigate or just reduce these interference. Okay, so the idea is the codebook design. So what is a codebook? It means that, for example, you see for user 1, there are 4 columns here, right? The 4 column represents 4 different informations. For example, if you transmit 0, 0, you use this code word. This is 0, 1, 1, 0, and 1, 1. Okay? You can transmit 2 messages, which means that you need 4 code words, right? 2 messages, 2 binary messages. So it means that we need 4 code words, right? So this is the codebook for user 1. This is the codebook for user 2. So, for example, user 1 wants to transmit a message of 1, 1. So I choose this code word. So what is a code word? Inside of this is actually a modulation signal. For example, the QPSK signal or a BPSK signal, something like this. Okay, it depends on how many messages you need to transmit. So, but I want to emphasize that only these 2 positions have actual signals to transmit. For these 2 positions, it just transmit 0. Okay, so let's say user 1 wants to transmit 1, 1, and user 2 wants to transmit 1, 0. So I choose the third code word, and he wants to transmit 0, 1. So I choose the second one, according to their binary messages. So after choosing for all the code words for all the 6 users, we just do the superposition for them. So we have the superimposed code word. We just add them together directly. So this is your transmitted code word. So each resource are actually a combination of 3 symbols. Okay, so each of the dimension is a combination of 3 symbols. Okay, so you can see this is a highly superimposed vector here. It contains the information coming from 6 users, right? So at the receiver, when you receive this code word, of course, we will have some noise here. And the receiver try to recover from this superimposed code word. So that will be very difficult because this contains all the information within a small 4 resources. So how to recover is a problem. But more importantly is how to design these 6 codebooks so that the interference can be mitigated. Okay, so that's a problem we are currently facing. So there are some parameters. I use K to denote the number of resources. I use L to denote number of users. And I use M to denote the size of the codebook. For example, we have 4 code words, so M is equal to 4 here. Okay. So the idea of this system is that K should be smaller than L, which means that the number of users is larger than the number of resources. That's the purpose we want to do, right? So the user number is larger than the resource number. Okay. And the other thing is that I use DV to denote how many resources can be accessed for a single user. For example, DV is equal to 2 because each user can use only 2 resources, right? And DV should be smaller than K, the total resources, right? So similarly, I use DF to denote how many users can share the same resource. So in this situation, DF is equal to 3, okay? Right? So the DF value should be smaller than the total user, okay? So I think this is clear for the description for the whole system, okay? So if we do it mathematically, it says that if I use this vector to denote, this is a vector, binary vector of length m. Oh, sorry, length log to m. For example, if m equal to 4, it means the whole book have a size of 4. It means that we have 2 bits here, okay? 2 binary bits to be transmitted. Okay, this is a bit transmitted. So how to map the transmitted bit to your code word? This function is the codebook we have, right? The codebook is a mapping function, maps the bits to multi-dimensional code words. Okay, so that's the thing we're going to talk about. Okay, so yeah, the next part would be the difficult part. The easy part has end. Okay, so there in the following there'll be some complicated part. So there are some low complexity design method. Okay, the first one is to map, because if you directly map the message to code word, that would be very complicated. So there are some low complexity design method. That is to map the bits to a mother code word. And the mother code word is times with a matrix that determines the resources and the shifting angles we have for individual users. That will be complicated, so we can directly use an example to explain this. Okay, the next page. Okay, for example, we have a figure, we have a matrix, this to denote the situation. For example, the first user, 1, the position of 1 denotes the position of resources it used. So the user 1 used the second and the 4th position of 4 resources. So this is the second user, this is a third user. Okay, so if we consider a QPSK signal here, there are 4 points on a QPSK signal, right? So, for example, C1 denotes the codebook for user 1. Okay, so the codebook user 1 can be like this. This is the first code word. A, B means these 2 points. This is the first code word, second code word. So it stands for the message bit of 00. This is 01, 10, and 11. Okay, so you transmit 4 code words according to the message bit you are going to transmit. Okay, so I use capital C1 denote the codebook for you, the mother codebook for user 1, and C1I indicates the ith code word for this. This is C11, C12, C13, and C14. Okay, there are 4 code words here. All right. So if we focus on user 1, we can build this matrix. This matrix is obtained from the, sorry, for the previous page, from this column, okay? From this column, okay? I don't want to introduce how to do that, but you can observe that the position of 1 is in the second and fourth position. So the matrix, the position of 1 is on these 2 locations. And I also use another matrix. It contains the phase shift information here. These 2 phases are not defined. So we can see what's the code word for user 1. Suppose we want to transmit the first code word for user 1. Then we just took the mother code word. Previously in the previous slide, the first code word is AB, right? A, point A and point B. So we took the first code word and then put it here and times it with the phase shifting. We have no idea why we need this, but we are talking about this later. We times it with the phase shift matrix and also this matrix. You have the first code word. You can try to see it actually put these 2 signals, shift 2 angles individually and put it into these 2 positions. Okay, so that's the idea of the structure of the codebook. You design the mother codebook. We'll talk about how to design this. And you design the phase shift angles and then put into the correct position. That produces the code word of the first user. Okay, these are some methods developed in the literature. The intention is to lower the design complexity. Okay, so we are going to talk about how to design the mother codebook, how to design the phase shift, and then put it into the correct positions, right? Okay, so here are some system models we might consider in this research. The first one is the okay. So this is the first. Sorry. Oh, okay, okay. So we see this is the system for a downlink system. So what is a downlink system? Let's see the system. First of all, each user have his code word, and then we do superposition for them, right? To have a combined code word. This is something we introduced before, right? So when we obtain the combined code word, then we transmit through a downlink system. This is a channel matrix, channel vector. Okay, so this is a channel vector for different resources. Okay, and then we have the noise. So eventually you have your receive vector. Okay, this is a downlink. So you see, after the superposition, we experience the channel. Okay. So the other thing is the uplink channel. The uplink channel, all the code words experience their own channel because we are now talking about the uplink. Each users transmitted their message individually, so they will have individual channels and received by the base station. So there will be some individual channels, and after experience the channels, then we do the superposition. Okay, so previous one, please. So if we look into the AWGN channel, if there's a situation that the channel quality is very good, if the channel quality is good, then you can imagine that this vector is because you know the fading means that the channel coefficient becomes large and small. It keeps changing all the time, right? But if the channel is constant, if the channel is stable, and the channel coefficient is exactly 1, then we don't see this part. Then it becomes an AWGN channel, which means that the superimposed signal you can directly add the superimposed channel with the noise. You can see the channel part. That will become an AWGN channel. So you can see AWGN channel is actually a special case of downlink channel. It describes the situation that the channel is stable. Okay, so we will talk about this situation because it's more easier to understand. Okay, next one, the next one. Okay, the next one. Okay, yeah. So here are the steps of our design. I will go through for this and hope you can catch it. Some basic ideas. The step one is to choose sub-constellations. Okay, we focus on the step one. Okay. And so how to choose the sub-constellations? We can use this figure. Previously, we see the F matrix. It indicates the resource occupied for a single user. But we can use another matrix to describe this idea. For this user, it uses two different signal sub-constellations. For this user, it indicates the position and also indicates which two constellations he is going to use. Okay, so actually, for each user on each positions, we can use different signal constellations. However, to simplify the design, I only use three different kinds of constellations: S1 and S2 and S3. Okay, so you can see on each resource, they experience. On this resource, we have the three constellations. On this resource, we also have the three constellations. Okay, so if we are talking about the combined constellations, actually on four different resources, they are the same. On this resource, the possible signal points are combined from the three constellations. Each of them can be, for example, QPSK. So when this user transmits a vector, the signal on this position is a QPSK signal. It's also a QPSK, it's also a QPSK, so it's a combined QPSK signal. But we can also use QPSK or 4PAM or a QAM, something like this is possible. So the benefit of doing this is that if we use fixed three constellations, the four resources will experience the same combined signal because it's all the three constellations, right? So it will simplify the design for the entire system. Yeah. So what I mean is that you can actually use 12 different constellations here, but instead we only use 3 of them. So, and the other benefit is that if you look into the first user used the 2 constellation, right? The second user used the same constellation, however, on different positions. So for the first user, you can see this user share the same resource here. However, they actually use different 2 constellations. Okay, so you can distinguish, more easy to distinguish the signal from different users. Okay, all right. So as I said that if we let A denotes the constellation we observe on a single resource, they actually comes from the same 3 sub-constellations. So imagine that there are 3 sub-constellations. So each signal is selected from 3 different constellations and do the combination to combine the constellation on a specific resource. Okay, so we can write it in this way. Yeah. Remember that on each constellation, we actually, for example, when we introduce this, if we choose the Codebook, we will experience some phase shift, right? Remember this? So this, it means that the signal on this point, this is first user, it will experience a phase shift. So is this, so is this, okay? So this is an example for user one. It uses these two positions. So on these two positions, they are the signals. For example, if I choose transmit this mother code word, this signal experience a phase shift of 1. This signal experience a phase shift of this. So this signal experience this phase shift. The other signal, which is transmitted on this resource, will experience another phase shift. So there are two phase shifts here. So similar to the second user, the third user, the fourth user, like this. So the benefits of doing this is that because they are the same constellations, so I can assign the same phase shift. So if this is S1, the previous, sorry, maybe I can. Since for each resource, they experience the 3 constellations. This resource also experiences the same 3 constellations. So I can assign the same resources, so the same phase shift here, so that the combined signal, the combined constellation on each resource would be exactly the same. Okay, so inside of a constellation, each constellation point can be written in this formula, So for each resource. So I can easily decide the phi value, the theta value, so that this result, this criteria can be minimized. So I don't want to go further into the details of the criterion. This actually derived from the upper bounded error probability of the signal transmission. So, however, the idea is that if we can properly design the value, the DEF values experience on a single resource, we can minimize this so that we can minimize the upper bounded error probability on a single resource. So that's the idea of designing for the rotation angles. And so maybe you can speed up a little bit. So for the second part, that would be we have chosen the signal constellations. Or I don't really define what's the constellation here. So it can be anything, QPSK, PM, something like this. You can choose on your own. You can choose your own constellations. And then second step would be to design the rotation angles so that the error probability can be minimized on a single resource. The third step would be designing the codebook based on a single user observation. So on this part, the idea would be for a single user, this represents the signal constellation on the first dimension, and this is the second dimension. If we assume that they actually use the same constellation, these 4 symbols represent, for example, QPSK, there are 4 different points. However, to build a codebook, it actually a massing process between 2 constellations. So it can be, so for example, if this represents the symbol of the first QPSK signal, it doesn't really necessary to combine with the first one. It can match with the other one so that we can form 4 different code words. It's possible. So to build the codebook is actually a mapping process. There are several mappings. So how many mappings in this figure, in this example? We actually have the factorial of 4, okay, which is 12 possible mappings, okay? So how to decide so if the size of the constellation, sub-constellation is M, we actually have that much pairing possibilities. So T, if we have DV resources, these are actually the total possible combinations for the possible code word for single users. So how can we choose the optimal code codebook among these possible codebooks. We choose the codebook that can minimize this. So what is this? This is the code word. Okay, so for any two code words, we can calculate its distance. This is the distance between two code words. For example, inside of codebook, we have 4 code words. So the combination of 4 choose 2, that is the number of pair we need to consider, right? So choosing 2 from 4 code words. Okay, so choosing 2 from M code words, that's the pair we have. So for each pair, we calculate its distance. So the value of distance actually affects the performance. Okay, so we want to find find the code word, the pair with minimal distance and maximize it. So the code word that the combination that can maximize in this is the optimal codebook we have here. Okay, so that's the idea of designing this. So, but we don't have enough time, right? So in the following, I will briefly introduce how we get at the end. And but because the design process is a little bit complicated, so I think I can just skip this. So there are actually several design steps here. Okay, so we only goes to the 3rd step, so there are still 2 steps remains, but I think we can skip this. So I will skip to the final result here to see what we have here. This is the design result. This is the proposed codebook, and this one is the original SCMA system proposed by Huawei, the company from China, right? This is the original SCMA codebook without design. I don't know how they obtained this, but it's obviously something not designed. So the properties design, this codebook can achieve a large gain comparing to Huawei's codebook. And so this is the actual design metrics. As you can see, our codebook can achieve the best design metric. This design metric actually indicates the performance on highest region. So you can see on highest region is much better than the previous result. However, this design also take care of the lowest region. This is the metric that indicates the performance on lowest region. So you can see in lowest region, we are still better than others. Okay, so but I don't have time to introduce the detailed design criteria. So we can also do, this is only for uplink AWGN channel. We can also do it for the uplink channel. And I have derived that the design step can be simplified for uplink channel. So if we directly see the result here, yeah, actually, I want to describe this, but maybe we don't really have time. So if, but you are an undergraduate student, so you don't understand the idea. It's actually, the design is actually involving a technique called space-time code. If you're interested in wireless communication, you all know about space-time code. I just transfer this problem into a space-time code design problem. So you can see here, the result is like this. So I have derived and proved that for this system, the slope is fixed. You cannot change the slope. However, what you can change is the position of the horizontal position of these curves. So you can see that although they have the same, comparing to the old system, although they have the same slope, however, the shifting is better comparing to the previous results. Okay. And okay. And if we talk about, we can generate this system to MIMO system. So we're talking about MIMO SCMA system. So in this case, each user will have multiple antennas. The receiver also have multiple antennas. So in this situation, I have proved that in this situation, by properly design the codebook, you can actually change the slope of the BER curve Previously, we cannot do this because it's a seesaw system. But when it comes to MIMO system, we can actually change the slope so that you can see on the final performance, the design system have a steeper slope comparing to the old one, so that we can have a huge gain between the proposed one and the conventional one. All right, so they are very similar situation in the downlink situation, but we don't have enough time, so I just skip this. But you can see the downlink system also have a very similar phenomena here. It have a steeper slope on this. So after this, the MIMO system, we can actually use some artificial intelligence method, such as the reinforcement learning. This is a reinforcement learning, and in each step, it chooses a better path to optimize the design criterion. And we see this each step representing determine a single real value and a single symbols on a single position for a single codebook. Okay, so it means, for example, on this stage, it means that we have assigned a real part and imaginary part signal for a specific position on a code word. So you can gradually construct a complete codebook here. So that using these, so we can also use deep learning method. Okay, for the deep learning method, the output layer represents the signal on codebooks. So you can do this, and we have a back forth method to update the weight inside of the neural network, and gradually you can design the codebook on the final stage of the output neural network. Okay, so using this method, you can see previously we say we don't really decide the signal constellation for different users, right? But we also say they can be, for example, QPSK and PAM, something like this. But these signals are regular signal. They have fixed signal points, regular fixed signal points. But you can see the output using AI-based model to design the signals, it becomes some random signals. For example, we see for a single user, we use 2 resources, right? So for the first user, it uses resource 2. The signal is like this. They are even overlapped point here. And user 1 also use resource 4. So on another resource, the constellation becomes something similar to QPSK. Okay, so these are the output of using the design using AI-based systems. So you can do that. It further enhance the performance. For example, it's a AWGN. This is the previous one, and this is the result obtained by using AI-based system. Okay, so you can further enhance the system design using AI system. Okay. All right, so these are the result for the uplink channel. And these are the BR performance of the uplink channel. So I have a quick review about this topic, the NOMA, codomain NOMA SCMA. This is a new technology used for multiple ASICs to put more users into limited resources by properly design the codebook utilized in for different users. So we consider different channel environments, including AWGN channel, uplink, and downlink fading channels. Okay, so we also use artificial intelligence technology to help the system design and improve both the BR performance and the design complexity. Okay, so the future work contains, we are currently doing the design for right-hand fading channels. Because you see, the right-hand fading channel means that we have a direct path between the transmitter and receiver. We have less reflection and path, right? So that is the feature for the modern communication system. For example, the wave system or terahertz communication. These are the feature of these systems. So that if we can successfully build for right-hand channels, then we can integrate these multiple access system to wave and some risk-based applications. And also possible future work is the power imbalance SCMA and grain-free Grant-free means that there are lots of machines they want to transmit through the base station without doing handshakes. So this is also very suitable for MMTC applications. All right, so this is a very brief introduction of my research work. If any of you interested in the contents, please feel free to contact with me. Thank you.
So do you have any question? Maybe I just have one small question. It's just a general. In terms of research, how mature the SCMA is? I mean, has it been adopted in 5G or the research is still on progress?
Well, that's a very good question because in current 5G system, even in 5G system, we don't have NOVA actually utilized in the spec, right? Yeah. But actually, they are still keep talking about the possibility of whether it will be used in 6G and beyond. Yeah, and so I can only say we still have a strong confidence that it will be utilized. But the question is, codomain NOVA is actually not the main trend for NOVA system. Usually they talk about power domain NOVA. Also, yeah. So but the problem is the power domain NOVA, I think, have some disadvantages because in power domain NOVA they use different power to do the combination, but they cannot support a large number of users. Yeah, that's the problem. But its advantages is more easier to be implemented. But if we are talking about, so that is why I doing research for the grant-free situation because it supports a large number of users. I also doubted which possible direction it will be actually adopted in 6G. I think the grant-free situation, the grant-free application will have more chances, yeah, because it can support, the feature of this is to support a large scale of users. Yeah, but that's only my guess. Thank you.
Okay. Thank you for Professor Yen-Ming Chen for his guest lecture. So if there is no any further questions, let's end this session and let's give applause.
Thank you.
Thank you.